Okay, let's talk about special topic 2410, which is the gradient operator, which sounds like a great name for a spy or something like that. 007, the gradient operator. So, relationship between E and V, right? E is dV ds, right? dr, this could be, dV dr, or, if the electric field is changing as a function of x, then it would be dV dx, right? Or if it's changing as a function of y, it would be dV dy. Or if it was changing as a function of z, it would be dV dz, whatever the case might be. But what if the electric field is a function of both x and y and z, that the electric field is changing in all three directions? So let me, so here then we end up having to use this, the gradient operator. This is del. Meet del, it's an upside down delta. It looks like this, and so it's negative del of V. Right? That would be what the electric field is. And really it's this always. It's just that we usually only have one of these things where the electric field is changing, right? Or dr or something like that. And so this is not something that, as far as I know, has ever shown up on an AP test, but it is in the AP curriculum, and so we have to cover it. All right. And what this is, del V, the gradient operator, the way we find this is it's, since we have more than one variable, we have to take what we call the partial derivative. So it's negative, and then this is going to be dV, dV dx. And this is the partial derivative of v, but with respect to x. Right? So I'm taking the derivative of this function, whatever it is, but only with respect to x. Right? I'm treating x, y, and z like variables. And then what I end up with here, that'll be in the y direction. Plus, and I have dv dy, that'll be in the j direction. And then looks kind of like a little d, right? dz, and that is going to be in the k direction. All right? So these are all partial derivatives there. Okay. Let's see. Okay. And so now we've got this example, example 1. So v, here's our function for the voltage. It's 3x to the fourth. They're playing the movie really loudly in the next room. Plus y squared. It's a Dead Poet Society, so at least it's something good. And then minus z cubed. Okay, and we want to find E. We're looking for E at 1, 3, 2, like at that point. Okay, and so here's what we do: dV dx. So then dV dx, these are going to just be 0 because I treat those like constants, and this ends up being 12x cubed. All right, dV dy. So then this is a constant, that's a constant, those will be 0. This would just be 2y. And then dV dz is going to be negative 3 z squared. Okay, and so now what I do is I plug in 1 into here, 3 into here, 2 into here, right? And so I get, so the electric field is going to be the negative of this thing, 12, 1 cubed, plus 2 times 3. This is I, by the way, j, plus, and then negative 3z squared. This is z. So negative 3 times 2 squared, and then that's in the k direction. Okay, and so what we end up with, this ends up just being 12, 12i. Let's get rid of this thing. So minus 6j, and that ends up being positive 12 Okay, so that's the electric field at that point where the voltage, the potential, electric potential is given to us by this function. Okay. All right, example 2. Example 2 works the same way. Okay, V is 3x y squared z cubed, and we want to find E at 1, 3, 2, just like before, right? Except now, so dV dx. So now if I treat, again, these things like just constants, then this ends up being 3 y squared z cubed, right? That's it. dV dy. This now becomes 6xyz cubed. And then dV dz is going to be, I bring the 3 in front, so this is 9xy squared, right? X and y stay the same because they're constants. And then I have z squared. All right? And now I'm plugging in all these numbers here. So I've got negative 3 times y squared, y is 2, times z cubed, so this is 2 now cubed, sorry, this would be 3 squared, I, plus, and then this, so this is now 6 times x, which is 1, times y, which is 3, times z, which is 2 cubed, that's in the j direction, plus, and now I've got this, 9x, which is 1, y, which is 3 squared, and then z, which is 2 squared, all in the k direction. Okay, and when you work all that out, what you end up with is negative 216i plus, or rather minus 144j minus 324k. So this is the electric field, in units, volts per meter or newtons per coulomb, either way. This is the electric field at this point where this is the function telling us the potential.